Hi, my name is Madhav Mittal and this is my FYP video titled React-based web application for stock price forecasting with a novel starting algorithm. So accurately predicting the stock market could help traders incur significant profits. Stocks are most important for many reasons. May it be investing to keep aside funds for any future calamities, retirement, or to earn a quick buck through daytime trading. However, intrinsic volatility in the stock market, coupled with its nonlinear and dynamic nature, makes the task of stock price forecasting challenging. Predicting trends in the stock market prices has thus been an area of research for many years. So this paper aims to describe an extreme gradient boosting or XgBoost based forecasting model using the XGB regressor library by finding optimal data features and hyperparameters required for the task of stock price forecasting. Additionally, the paper aims at designing a cross-platform React app based on the Redux architecture and integrating it with the XGBoost model using Flask. So, now, React for our web application, we have chosen React as the primary software to create the web application. It specifically aims at achieving the best possible rendering performance. Highcharts is a JavaScript-based data visualization library. The application uses highcharts as it provides intuitive functions to plot many interactive charts. The UI functionalities are handled by Bootstrap. An application designed for the purpose of tracking stocks are required to be dynamic due to the volatility of the stocks. An architecture that can help with fast and reliable state management is necessary, since the app state is updated frequently. The React Redux library enables the design of a fast, scalable, and dynamic application. The React Redux library helps set up the Redux architecture in the app and helps the React components interact with the Redux store. So this is our final application's homepage. It is implemented in dashboard home.jsx and it is the homepage or the landing page of the app. It displays information about the functions available for the user in the form of Bootstrap cards. So this is our Navbar page. The Navbar allows the user to switch the views within the app. It lets the user go to the home page or the stock exchange page, which includes the daily, weekly, and monthly charts of the requested stock, or the predict page, which predicts the stock value. This page is implemented in the file highchartsmenu.jsx. So these are the daily, weekly, and monthly pages. All these pages are part of the stock exchange that will allow the user to view the daily, weekly, and monthly charts of the requested stock. These charts are interactive and allow the user to zoom in and self-certify dates within which they want to view the stocks. So this is the monthly comparison page, which helps us or the user visualize and compare differences between the stock values of the specified stocks. Here, the specified stocks are Pfizer, Microsoft, Apple, and Google. This page is implemented in the file monthly stock comparison.jsx. So this is a prediction page which runs the stacked XGBoost model in the Flask server according to the user specified parameters and returns an image of the prediction as it can be seen in the image. So now we talk about the experiments on how we implemented the XGBoost model. The models predicted the values of Pfizer stocks denoted by the ticker PFI. Predictions were made every 10 stock days on the validation dataset. A forecast horizon of 21 days was set. Thus, for every prediction, a forecast for the next 21 days or one calendar month was made. A total of 24 predictions were made on each dataset as shown in the table. Feature standardization is an essential part of stock price predicting algorithms. Models trained without scaling of features always output predictions within the range of the prices present in the training set. Thus, for each forecast, the input features were scaled to have a zero mean and unit variance. The predictions were then made on the scaled feature set. Predictions made on the particular day are used as input values for the future predictions. Thus, for the input dataset had to be updated after every prediction. The corresponding flowchart can be seen and followed as in the figure. Now we have done several types of feature engineering for our model. The first is daily returns. The signal must be made stationary prior to making predictions. Thus, the raw stock prices were converted into a new feature called the daily returns. The daily returns measures the dollar change in a stock's price as percentage of the previous day's closing price. Now, the next feature is daily returns using time lag. And since the daily returns of the current day is highly correlated to the daily returns of the previous day. Thus, the daily lags of the previous 10 days were used in the predictions. Now, the next is date-based features. The stock price data is a time series data. Thus, for the information about seasonality trends is very important. To learn how the market fluctuates with different days, weeks, months, new features were built using the fast AI library. The last features are the technical features. Since the paper involves stock market data, the technical indicators provide the model with invaluable insight about the patterns present in historical data. Thus, a variety of technical indicators were introduced for the model. Additionally, each technical indicator had many dedicated features. They were created by either increasing the corresponding rolling window, lagging it to get the previous day's indicator, and getting information about the bullish and bearish crossover signals. So now we define the training, validation, and the test dataset. The dataset was split into training and validation as well as test data. The training data was used for model training and the validation data was used for hyperparameter tuning. Finally, the test data was used to assess the accuracy of the model. The training dataset consisted of 3 years worth of market data, which translates to about 76 calendar days, since there are roughly 252 trading days in a calendar year. The validation set used the following year of the data to perform hyperparameter tuning and thus consisted of 252 days. Now, we built the XgBoost model using the XGB regressor Python library these models were initially trained using the default XgBoost parameter values as can be seen in the right figure. The XGB regressor library contains built-in methods that help with model training and testing. The procedure for building the models as well as hyperparameter tuning remain the same across the models. However, the features used with different models were different. Each model was built using a subset of the features defined during feature engineering. Now, the way we build that stack model is a bit different. Model stacking is an ensemble-based algorithm that combines the output of several machine learning algorithms. The outputs from the individual learners are run through another machine learning model called a meta-learner. The meta-learner optimally combines the model predictions, thus minimizing the weaknesses and maximizing the strength of each model. This paper used XgBoost, SVR, and regression as the base learners, with regression as the meta-learner, as it can be seen in the figure. Now, hyperparameter tuning involves choosing a set of optimal hyperparameters for the learning algorithm. It was performed on the validation dataset. XgBoost has several hyperparameters that can be tuned, as can be seen in the figure. After obtaining all the optimal hyperparameters, final predictions were made on both the data validation and the test dataset. Now we talk about the results. The following metrics are used to evaluate the precision of the model. The first is the root mean square error, the second is the mean absolute percentage, and the third is mean absolute error. The last value method is implemented on each of these metrics to benchmark the result. It must be noted that only results after hyperparameter tuning are shown in the following slides. So these are the results of the last value method model. This model returns high values on RMSE, MAPE, and MAE. This can be attributed to the fact that last value algorithm is a naive algorithm that assumes zero volatility in the data and thus sets all forecasts to be the value of the last observation. This is followed by the model with only lag returns as features. The model does not make optimal predictions. It is unable to predict the variations in data and therefore day-to-day predictions do not differ that much from each other. This can be attributed to the fact that the dataset consists of the features only created from the daily return of the past 10 days. Thus, the model is not able to capture other information within the dataset. The model thus would benefit from a dataset with more informative features to ensure sufficient complexity for accurate forecasting. This is followed by the model which consists of date features. This model outperforms the previous model since it was provided with more contextual features. However, the prediction still suffers from a low RMSE. This can be attributed to the fact that although the model now has a relatively higher day-to-day stock value range, it still predicts a downtrend incorrectly. Now we talk about the model with technical indicators. This model improves the accuracy over the previous models. It can also be seen that the model understood the trend, but the exact closing values were predicted incorrectly, as it can be seen in the test prediction, the second image in the slide. This is the last model, which is the stack model. This model predicts the trends correctly and predicts the prices within an acceptable range of error. It, therefore, outperforms all the previous models. These are the final results. As it can be seen in the bar chart, the stacked model makes the most accurate predictions and thus has the lowest overall error metrics. The left figure visualizes the predictions made by the initial model and the stacked model. The initial model was unable to predict the trends correctly. It did not capture the volatility within the stock data. The stacked model, on the other hand, could predict both the downtrend and the uptrend. The predicted stock prices were close to the actual stock prices, thus indicating that the model captured the volatility present in the data. We now talk about the conclusions. Firstly, it was seen that as more complicated and context-rich features were added to the model performance improved. The models with seasonality-based features and technical indicators helped the model learn trends that were otherwise not prominent. Secondly, it was seen that throughout the modeling process, hyperparameter tuning had a significant effect on the model performance. It made the models more stable by stopping overshooting and decreasing the errors considerably. Thirdly, it was observed that the stacked model provided with the most robust and accurate model. It followed the trend line closely and delivered a low error rate. Thus, it was concluded that the stacked model provided the best results and thus was most suited for the job of stock price forecasting. Thank you.